Hi everyone, thank you very much for being here today. My name is Iker Liceaga. I'm a mechanical engineering intern at NASA Goddard Space Flight Center, and I'm here today to talk about the Neutron Spectrometer we have built for small satellite opportunities. And in particular, I want to talk about how we have built and integrated this instrument within a 3D CubeSat we have been developing in collaboration with the New Mexico State University. So let's talk first about the scientific motivation for building a neutron spectrometer like this. The neutrons that we can find in the heliosphere are basically mainly produced in two different ways. The first of them is called QRAM, which stands for cosmic ray albedo neutron decay. And it is basically cosmic rays going into our magnetosphere or into other planetary atmospheres too, and producing electromagnetic shower that as a byproduct also produces albedo neutrons that we can potentially measure in the case of Earth with a satellite placed in low Earth orbit. And the second way of neutron production in our heliosphere is solar neutrons, neutrons that are produced in the surface of the Sun as a result of the activity of the solar flares. But the problem of trying to measure these neutrons is that their half-life is more or less 15 minutes for the fastest ones. So to measure the low energy neutrons, we need to be very close to the surface of the Sun. So that poses a challenge, a very big challenge, and that's why with our neutron spectrometer, we would like to focus on the first type of neutrons, the neutrons produced by QRAM, by cosmic rays. So having talked about which neutrons we are going to target, let's talk a bit about how we will actually measure those neutrons. So here I will try to give you an overview on the topology of a typical neutron spectrometer. So normally what you will have is what is called a double scatter instrument, which is an instrument that has two neutron detectors inside. And the point of having two detectors is that you can detect the same neutron with some delay between the two detectors. And with that delay, you can actually calculate the velocity of the neutron, and thus you can also calculate its energy. That's how you do neutron spectrometry. And since we are talking about CubeSats with limited space, it is also noteworthy that we will try to maximize the volume of those detectors as much as possible because the scientific performance is directly proportional to their size. And also in terms of size, we will need to make room for what is called an anti-coincidence detector. So normally, the materials that we use in neutron detectors react not only with neutrons, but also with electrons, with protons, and with gamma rays. So we need to somehow differentiate those three signals from the neutrons in order to focus on the science we want to do, right? So to somehow subtract the electrons and the protons from our signal, we use this anti-coincidence detector, which is basically a detector, a secondary detector surrounding the first primary detector that is thin enough to let the gamma rays and the neutrons go through it, but is thick enough to detect the protons and the electrons, so that, as I was saying, we can subtract those from the signal we are getting in our neutron detector. And to understand how we are going to differentiate gammas from neutrons, we need to look into how the actual material of the neutron detector works. So that material is normally a scintillator, which is a material that produces light when a gamma, a neutron, an electron, or a proton goes inside the material. So in order for us to differentiate gammas from neutrons, we need to look exactly at how light is produced inside the material. So here in the slide you can see an equation, and here on the right you can also see a pulse shape. This pulse is how it is the light profile of the scintillator when a gamma ray goes into it or a neutron goes into it. And you can see how the pulse is a bit different when you have a gamma ray or when you have a neutron. With gamma rays, the pulse is a bit shorter. So that's how we can actually differentiate them, looking at the light profile. And this is called the pulse shape discrimination. And in the last plot, you can actually see how we can differentiate very well neutrons from gammas, getting both spectra. And we have talked about how we are going to produce light with the scintillators, but we have not talked about how we are going to convert that light into an electrical signal that we can handle, that we can measure. So traditionally, this has been done with what are called photomultiplier tubes. But the problem with these photomultiplier tubes is that they are very big, very massive, and they are traditionally very difficult to fit into a nanosat like a CubeSat. So what we propose, here is the novelty, is using modern silicon photomultipliers, or SiPhos, which are much lighter, have a much lower volume, and especially they operate with much lower voltage and power. So they are ideal to be fitted into a CubeSat layer, like the ones we are discussing in this conference. And they consist of arrays of small avalanche photodiode cells of a thickness of more or less 15 microns. As you can see in the pictures, their scale is ideal to be fitted into a CubeSat. And the other advantage is that you can basically arrange them in any size of array so that you can fit any footprint that you may want. So now that we have understood the principles of a neutron detector, let's talk about how we have applied those ideas practically. So here is INCA, which stands for Ionospheric Neutron Content Analyzer, and it is a CubeSat, a 3U CubeSat, that is being developed in conjunction with the New Mexico State University. Two of the 3Us are filled with the neutron detector, which is highlighted in the slide. This neutron detector is being developed at NASA Goddard, and the U left accommodates all the spacecraft electronics, the attitude control system, the batteries, all the systems, and that is being developed by students at New Mexico State University. And there below you can see the basic structure of the detector. You can see how we have two scintillators, two cylindrical scintillators in white, to match the double scatter schematic I was showing in my second slide. And you can also take a look at the 4x4 silicon photomultiplier array that we are going to put under each scintillator to collect all the light that those materials are producing. So let's talk now a little bit more about the mechanical design of the neutron detector. As I was mentioning, we will have two cylindrical scintillators, p-terphenyl scintillators. Under them we have 4x4 silicon photomultiplier array, and taking advantage of the space that we have in the middle of the two scintillators, we have put the electronics to capture the waveforms that we are getting from the silicon photomultipliers, which is, in this case, is done with an ASIC called the RS4, developed by Paul Scherrer Institute in Sweden, and then sends the waveform signal to a post-processing unit outside the detector, which in this case is a bigger one. And here, it is also noteworthy how we have designed the anti-coincidence detector. It is a box, the brown box that you are seeing below, that surrounds the primary instrument. It is constituted by very thin scintillator panels that, as I was saying, somehow block the electrons and protons. And the clever thing here is that we have beveled the corners of that box in order for us to put a small silicon photomultiplier arrays in the corners without affecting a lot the cubic shape of the envelope, so that we can still fit the instrument into the CubeSat structure. So here you have some pictures of the mechanical assembly of the prototype. In the first picture you can see one of the p-terphenyl scintillators I was mentioning. You can also see its corresponding 4x4 silicon photomultiplier array. Then you can see also in the second picture how we have put one scintillator against the other, how we have filled the space in the middle of the tube with the electronics to capture the waveform, how we have closed everything up. And in the lower row, you can actually see one of the panels of the anti-coincidence system. You can see also how we have beveled the corners so that we can put a 2x1 a silicon array to measure that corner, and you can see also the final assembly with all the wiring in place, ready for testing. So before doing the final testing, we needed also to calibrate our instrument, and we needed to calibrate it with gammas and neutrons, because remember that we are trying to differentiate very well both of them with the pulse shape discrimination. So with the gammas, we just bombard our instrument with different gamma ray sources of known energy levels, and we associate those energy levels with voltages that we are getting in our instrument. And we try to do the same thing with neutrons, but with neutrons is a bit more tricky, because the neutron beam we have doesn't provide a monoenergetic beam. It has many energies. So in order for us to be able to pick discrete energy levels, we needed to modify the angle between the instrument and the neutron beam subsequently to do exactly the same as we were doing with the gamma rays, which is associate energy levels with voltages that we are getting in our detector. So once that we have completed this calibration, we conduct the final testing with the Californian 242 source, which is providing us with polyenergetic neutron beam and gamma rays, and we are able, as you can see in the plot, to differentiate very well neutrons from gammas, so that we can look at the neutron spectra, and measuring also the time of flight of neutrons and gammas, we can differentiate them even better, right? So regarding the current status of this project, we have done already the pre-integration of the spacecraft part and the instrument part in New Mexico, actually last week, May 22nd. We are doing some fine adjustments in the neutron detector, expecting to deliver it by June 15th, and the environmental testing and the mission readiness review of the whole CubeSat are scheduled for July of this same year, and the spacecraft delivery to the launch provider is scheduled for September. So well, this was all about my presentation, and thank you very much for your attention, and I will be happy to respond to any questions that you may have. Thank you.
Any questions?
Sorry, perhaps you already mentioned it, but what is the scintillator for actual neutron detector, and then also your anti-coincidence field?
It's p-terphenyl. It's a plastic.
Oh, plastic, okay. Yeah. And do you have any targets in your mind for this project?
Targets regarding what exactly? Energy levels or?
Yeah, target for the planetary target, and also energy range you can cover.
So the energy range, the dynamic range, is from 1 MeV to 10 MeV neutrons. That's the energy target. And this neutron spectrometer is valid for magnetosphere or Heliophysics, and also for other planetary atmospheres.
Thank you.
Any further questions?